This is just one last Outlook slide to cover a few things that people are doing research on in the last few years, and still open questions around deep reinforcement learning and making it really applicable in application, because it's still very difficult to get it to work and to achieve stable performance and so on, as we've also seen in our exercises. So yeah, the first point is about data collection. We've seen that it can take quite a while to train an agent, even on a very simple task like card pole or this frozen lake. And that's mainly because the agent has to learn from and collect data at the same time. And collecting data takes a long time. And these are very simple environments, very simple problems. If the problems are more complex, this will very quickly become very slow and a bottleneck. And so one thing that lots of papers are focusing on is how to improve that. In particular, if you have a simulation of the problem. So if you can, you don't have to wait on the real world to run your experiments, but you can simulate a problem and then run lots of collect data in parallel. So one thing that people are doing is just parallelize the simulations so that you can run simulations across multiple machines, simulations of the same environment, and run the same agent, copies of the same agent in each of these environments, and so collect episodes in parallel. The advantage is that, as we've seen, often when our update depends on having at least one, ideally multiple episodes of experience. And so between updates, we can collect multiple episodes in parallel. We don't need to wait for one episode to then run the next episode. We can just collect 10 or 100 or 1,000 episodes in parallel. And if we have 1,000 episodes and perform our update based on that, that's a much better update than if we just have one episode, which is much more biased. So that's one obvious thing to do. However, if you then scale this up a lot, you run also into problems with communication. So you need to update each copy of each agent, and you need to centrally collect all the data that you collect and so on, and that can get difficult. So people are, in addition to that, also looking into how can we distribute the training itself. So how can we train multiple copies of agents on different machines, and then synchronize the updates that happen on different machines in one central parameter server. So that's one avenue. This is applicable wherever you have simulations and where running the simulation is time consuming. Another thing is learning from demonstrations. So what if you have lots of data, maybe just randomly recorded data, maybe data from a system that is already working, that you're trying to improve with reinforcement learning. So you can just collect data from that system and use it as demonstrations. Then you have the problem of that you want to train off policy. So the data is not produced by the agent itself. It's produced by something else, and you want to make use of it. And there are whole subdomains of reinforcement learning. For example, imitation learning, which is given a bunch of demonstrations. How can I train a policy to imitate what I see in these demonstrations? Or inverse reinforcement learning, which is about something similar, but more specifically about learning a reward function from demonstrations or just any observations. It doesn't have to be expert demonstrations. It can just be anything. And so you're trying to infer from these observations, you're trying to infer a suitable reward function to then subsequently train a reinforcement learning agent. So it's basically about automating learning reward shaping. So we've seen reward shaping, but we've hand engineered our reward shaping functions. But what if we can infer that from data, a suitable reward shaping function? And yeah, obviously in many real world problems, there might be lots of data around, but you can't run an untrained agent in the real world applications because it would just take thousands of episodes of crashes before it learns anything, and that's not doable in many real world applications. So being able to make use of this off-policy static data is very useful. Yeah, then we have a point on internal state. So what do I mean by that? All agents or all policies that we've looked at so far, they were really just a reactive policy. So they were given a state and then they were outputting an action. And these policies, they can't, the way we implemented them, they can't remember what happened before in an episode. So every time they're given a state and outputting an action without any context. And that's of course not ideal. Ideally, you want the agent to know what it did before, to know what happened before, because that enables more sophisticated planning and yeah, leads to an evolving decision making as opposed to a purely reactive decision making based on the current state. And to do that, there are in deep learning, there are a class of modules called recurrent neural networks. And so maybe you've heard about LSTMs also, long short-term memory, which you can apply there. So to give the agent an internal state, some sort of memory that evolves over time, and that makes it possible to remember what happened before and to, in that sense, enable planning, longer-term planning. But that complicates the algorithmic side a lot, because now you don't have independent time steps where you're just inputting a state, outputting an action, but now you have this internal state that you have to carry from time step to time step. And that's, yeah, in terms of implementation, that becomes a bit more complex. Another point is around predicting the future. Now, obviously, if an agent reasons about what might happen, how might this environment or this problem evolve, is a useful thing to think about when you decide what to do. And so something that people do, for example, is to just, in addition to train a policy with policy gradient or Q-learning, you can add additional auxiliary losses to just predict the future. So just, okay, given that this is the current state, what will the state in the next time step or in 10 time steps look like? And this is just providing an additional training signal with the idea that this is also something meaningful to learn, and it has synergistic effects with learning a good policy. Learning what happens in the future is helping the policy learning. In particular, if we have sparse rewards. Sparse rewards means that we don't very often get a signal how well we're actually doing, and then having this auxiliary information, auxiliary target signal is very useful. And another thing why predicting the future might be useful is to around the concept of curiosity or surprise, which is if we want to explore, we've talked about Q-learning having this epsilon greedy exploration, so just every now and then do a random action, which is not very targeted. We talked about policy gradient, incorporating exploration as part of its training, which is still difficult. How much do I want to explore? How much do I want to exploit? And predicting the future is one way of making exploration a bit more meaningful by saying, whenever I have difficulties to predict the future of what might happen if I take this action, this is probably an area of the state space that I don't know very well yet. So I might either want to avoid that if I don't want to be curious and say, stay safe, or I might encourage that during training to say, try out in particular what you don't know very well yet. So the things that you are able to predict very well, don't really collect more data there because you already are able to predict that very well. And again, this is very helpful for sparse rewards when maybe a bit similar to Frozen Lake, when it's maybe a long way to find the goal, you need to somehow encourage the agent to make progress without it really receiving rewards from the environment. Yeah, then we have goal parameterized policies. This is in particular interesting in context where you might have multiple objectives, or you might want to prioritize behavior differently. So the way we looked at reinforcement learning so far in the classic formulation is that there's the environment, and the environment has one idea of what is good, and this is rewarded with this one continuous value that you get, the reward signal. However, real-world applications are often a bit more complex than that, and what is good in at one moment might not be the most desirable in another moment. And so that's the idea where you say, instead of just providing one reward signal, one single value, can we somehow incorporate a goal into our policy? So make our policy aware of the goal and hence be able to control the goal, to change prioritization of what to optimize for. And that's also, again, a kind of subdomain of reinforcement learning that looks into how to do this. And finally, for this list, there are, in the very beginning, we talked about model-based versus model-free, and all we talked about are then model-free methods. And the reason is that really in deep reinforcement learning, most of the literature in the last 5 years or so focused on model-free reinforcement learning. But there's obvious appeal around model-based methods, or at least influences, because if we know about how our application works, it seems to be stupid to not make use of that knowledge and somehow try to incorporate the things that we know as practitioners about our domain into the algorithm. However, that's not always easy, because all the methods that we can find in the literature are model-free, and so don't really allow for infusing any environment knowledge. And so there's a domain of how can we use the model-free methods but make them a bit more model-aware. And one way to do that, for example, a very general way, is to learn a world model. So to use machine learning to also learn a model about the environment in addition to training our agent. It's a bit like predicting the future. So you learn how the world works, and if you learn that very well, then you are able to use that knowledge in training. And in some extreme cases, people have been exploring training an agent completely based on this learned world model. So the agent will never see the real world, or will never see the real problem environment, and will only learn based on this model of the world. And only then for evaluation, it will be set loose in the real problem environment and is then able to perform well, even though it has never ever encountered the actual problem environment, just kind of learned versions of it. And yeah, that's another avenue that people are very interested in. And I'm sure there's a few other avenues that we've missed here that are also researched a lot. In general, deep reinforcement learning is a very active field with lots of research happening right now. And it's very hard to keep up with all the literature. Are there any questions to any of these points? If not, it's late enough, so then we can conclude with our one final announcement from side of Blue Prism. We are also hiring concretely for a senior AI lead position, a research engineer position, and software engineer position. So if you're interested in that or want to know more, please reach out to us and we can tell you more about that, or visit that link. And yeah, then that's all from our side. Thank you very much for organizing this tutorial. And yeah, I hope you learned something.
Just one more slide, Alex, with the feedback slide.
And the very last slide, yeah, we would appreciate if you could fill out this very short feedback form so that we can improve this tutorial if we are to give it again in the future.
And I'll post
Can you
a link
put
in
the
the
link
chat.
into the chat window?
Yeah, I'll
yes,
drop
please,
the link in the chat as well. There you go.
All right, and that concludes the tutorial, I think.
Okay. I have to say thank you so much for this tutorial. Really much appreciated. So here's your applause. Yeah. Always funny to applaud people online. So I learned a lot, and I can only second what you said, that there's so much literature right now going on, and if you even have to are struggling to catch up with everything, oh dear. So let's see. But I think this tutorial is a good way to at least have a chance to catch up with everything that's going on in IR. So SIG-IR had, I think, I don't know how many papers mentioning reinforcement learning. My PhD student who's here as well, he's working on reinforcement learning, and I hope he listened to your job advertisement slide. He's finishing soon, just saying. Anyway, and there are probably some others who might be interested. I think this is a very exciting topic, and I see the potential doing some research on interactive IR, and myself, I think I see the potential how you can really model more user interaction into this, and I think that's very exciting. It gives me some inspiration. I have to also catch up a bit with some things here, but really very, very well done. So thank you very much. Is there anybody else who would like to, before you fill out the feedback form, say anything? What did you get from this tutorial today? Is there anybody who wants to?
Well, first of all, my brain is completely deep fried right now, but it was really interesting and informative, and I just like to thank all of you for this event, because I, for my part, really enjoyed it. Thank you.
Great, thank you.
Yeah, thank you.
Thank you, everyone. Thank you for your participation and your contribution to the tutorial. We had good discussions, and also I would like to thank Ingo and Haiming for organizing the tutorial. And BCS IRSG has been the home for the IR researchers in the UK for many years. So I really appreciate that. And I look forward to the Search Solutions conference tomorrow.
Yes, so yeah, two things. So yes, I'd like to thank Haiming because she was the main person who organized it. I'm just more looking at the whole search solution thing. And so yes, I hope to see many of you tomorrow. I think we start at 10, if I'm not mistaken, so a bit later than today, and with some exciting talks. And it might even be that you might even still be able to register if you haven't done so yet. It's a different link, so you should have received a second link for tomorrow's event. It's a different Zoom link. Yeah, I don't have too much to say. Again, many thanks. Yeah, enjoy the rest of the evening and hope to see you tomorrow then.
Yes, a big thank you from me as well for being here, and everyone. Sorry for missed so much of your talks. I'm going to catch up the recording because of my teaching duties. I had to leave for most of the part, but looking forward to learn all this. And thank you so much for your effort and to make this possible. Thank you all. Thank you, Ingo, as well, for chairing the meeting when I'm not here. Thank you. Look forward to see you tomorrow.
Yes, I think that's it then. So yeah, grab your drinks. Normally we have maybe not so much after the tutorial day, but after the main event we usually have a when we're in the BCS headquarters in London, we have a pub called the Lyceum Tavern where we gather usually after Search Solution. Unfortunately, not this year, but hopefully next year. So maybe we can repeat this next year, but this time then face to face and in some of the BCS rooms. Yeah, that would be fantastic. There will be certainly a Search Solution 2021 and with tutorials again. And probably we might get an updated version of this. That would be fantastic. Okay, so thank you very much, and hope to see you tomorrow. And if not, yeah, hope to see you soon, face to face, one day.
Thank you again. Sounds good.
Thank you, everyone. Take care. Have a great evening. See you tomorrow.
Thank you. See you tomorrow.
Bye.